Hey, my name is Kenneth. I'm doing a presentation on my project for the course Real-Time Systems. For my project, I'm doing a 3-band equalizer where I can individually change the amplitude of 3 frequency bands, baseband going from 0 Hz to approximately 300 Hz, a midband going from 300 to 5 kHz, and a treble going from the 5 kHz to 2000 kHz. And the whole thing will sample with a sampling rate of 44.1 kHz. So the first thing I was looking at was creating these FEAR filters, which is what I'm going to use for this project. So here you can see a FEAR filter with the red indicating the bass, the black indicating the midst, and the blue indicating the treble. This is 100 taps, and as you can see, this would not be significant enough because some of the bass band would go in with our midband. So I increased the tap number by 50 until I was satisfied. So this is 500 taps. I went up and made 1,000 taps, but I didn't think that the increase that the double of a filter tap would make this much deal, so I went with 500 taps. So after that I went into Vivado and created this. This contains of my 3 bands FEAR filter. Here my bass, midst, and my treble. These will be controlled with a rotary encoder, which you can see down on the board here. So as I rotate the rotary encoder, depending on what LED is lit, that band will then be changed its amplitude. By clicking on the rotary encoder, I can go through the bands and individually change the amplitude. The signal goes out through a homemade DAC, which is just a 12-bit resistor ladder. So the input signal is just a sample signal, which comes down from this block. So I have this VRAM block where I, in MATLAB, took 3 different sine waves. A sine wave with a frequency of approximately 170 Hertz, a sine wave of approximately 2.5 kHz, and then a sine wave of approximately 10 kHz. This made when you combine them, you can see a sine, so going negative also, which would represent a sound. I took this, made it 1024 taps long, not taps, but yeah, what's called samples long. That's what I did, and then I made it 12-bit up down. So this one is made into a co-file, which is then put into this ROM block, where I'm going through the addresses with this counter, which is again activated by this prescaler, which sends out a pulse with a frequency of 44.1 kHz, which is the sampling frequency for normal sound systems. So if we go out of this again, you can see that the signal goes into each of these 3 FEAR filters alongside with sampling, a pulse. So to change the amplitude, I have this block over here, which takes in the bare signals from the rotary encoder. This takes from a predefined fixed point binary number, which represents the amplitude as a real number, and puts it out on these 3 signals, which goes out of this block. So that's the real amplitudes, which also each and every one goes through a pipeline to reduce slack into each of the filters. After the filters, they all get summed up to make one signal, and because my DAC is unsigned, I have to add half of full 12-bit to get it up in an unsigned state where I can put it out on the 12 pins on the board. It also goes through a latch, again to prevent unknown or unwanted signal changes while the signal goes through. So if we open one of these blocks, you can see here this block, which is made in HLS, high-level synthesis. This is a normal FEAR filter equation where you have an input signal and the coefficients, where n in my case is 500. So the coefficients is, I've got them from MATLAB, where I showed you the filters. So that's the coefficient that will make this filter. For the base, that's put in here and here. So because I'm doing it this fast, I'm using 2 BRAMs, which has the exact same thing, so that I reduce the load time with half. So the signal goes in here, goes through another pipeline to reduce slack into a multiplier, where you can see the amplitude is coming in. So this is just multiplying the signal. Again, another pipeline goes out. So that's the whole system. Let's see it in action. So you might recognize this signal from the ones that we saw in MATLAB. So if I take this knob, this rotary encoder, and rotate it, you can see that some signals get higher. So if I take all signals and make them as low as possible, like this, you can see that now you see the signal is going way low. So if I take one, so this is the 170 Hertz, which you can see down there, approximately 170 Hertz, that it gets amplified. Take that down, change the frequency band, takes out the amplitude. This is the 2.5 kilohertz signal, and the last one, maybe have to zoom a bit here. You can see it's the 10 kilohertz that gets amplified. I can amplify it all, the signal at once, which gives me the original signal. So it works. I had a bit of problems with the slack time because of the amount of components that went into this. I'm almost using all of the FPGA, but yeah, works.